Okay. Welcome back. Some announcements. First thing is this Thursday is exam 3. So it's a hard exam. You're going to have to, if you haven't started studying already, I suggest the sooner the better. The sooner the better. Get going on that. If you look in exam prep, exam 3. So these, I think most of these quizzes are from a previous semester. So the way I would frame these is more practice. So lots of times students ask me, where can I see more practice problems, or that will help me with the exam? So this is what you can consider most of this stuff, which you had not seen before. More practice, okay? But in terms of centering your study, you want to center your study around this review outline and just ignore the dates, okay? Just ignore the dates. Just focus on the material. So we've done because we had the mastery exam in there, we've covered a lot of material since the last exam, since exam 2. Because it's been more than 3 or 4 weeks. Usually we have an exam every 3 or 4 weeks. Well, now because that mastery exam was in there, it was more like 5 or 6 since exam 2. So this review outline is going to be really important. Okay, so focus your studying on this review outline, and then written homework, web work, these practice quizzes, the videos are all going to be important resources for you to get ready for the exam. Same time and place as usual. So Thursday evening, you can arrive and start anytime between 6:15 and 8. Okay? You can arrive and start anytime. Well, I would say 7:30. So make sure, give yourself an hour and a half. So 6:15 to 7:30, and I'll send an email out if you cannot start the exam sometime between 6:15 and 7:30, then we'll need an alternate time for you. And if you have not passed the mastery exam, you need to do that, and you can do that in my office hours or Morgan or Cerny's office hours, but no other office hours. Just your recitation TA or myself. You've got to pass that mastery exam. And you can know that by if you have a 0 or no score in Blackboard gradebook. Okay, Allison's this afternoon, her office hours are canceled for this afternoon. Just be aware of that. She won't have her office hours today. There was one more thing I wanted to say. Regular recitations this week, right? But then we'll focus on reviewing for exam, okay? And then there's also something else, but it's short. So yeah, everything in recitation will be important for an exam. Oh, so and then Wednesday, so I've already posted that web work due Wednesday, these second bank of optimization problems. They're more difficult, so we're not going to do any more optimization in lecture, so you just need to get into office hours and get the help you need on those, okay? If they are more difficult, just want to warn you about that. Hope you started over break. Many of them deal with trig and angle measure, okay? And that's important, so get the support you need for that. Okay, any questions about all that important stuff? Okay, so we have kind of laid all the groundwork, all the building blocks for the fundamental theorem, and actually we've already talked about the fundamental theorem, but we want to return to that because it is the fundamental theorem of calculus. So we don't want to treat that lightly. And we were kind of in the midst of other things as we started first talking about that. So let's really hammer that home. So I'm going to kind of repeat a slide that we had before because I think it was a good slide, important slide, and we've had a lot in between. So let's review this idea that in the first half of the course, we looked at the situation. You know how fast something is changing, and you want to know how much of it you have. You know how fast something is changing, and you want to know how much of it you have. And here's an example of that. Over on the left is a rate of change function. It's the rate of change of elevation as a function of distance from the coast. Okay? So at the coast, elevation is 0. And then as you move away from the coast, this is the rate of change of elevation in 100 feet per mile. 100 feet per mile. And then on the right, we have the elevation function. Okay, also distance from the coast in miles, and then elevation in hundreds of feet. And we want to think of that as an amount function, an amount. So this is the amount of, thank you. An amount function. It's telling us how much elevation there is at a certain number of miles from the coast. How much of it do we have? So we think of that as an amount function. And so here's the setup. Using the exact rate of change of elevation from R, write a function f that gives exact accumulation of elevation starting from a miles to x miles from the border. So we could come along here and just pick some a miles from the coast. So that should be from the coast. Okay, so here we are, a miles from the coast, and what do we want? We want a function that starts accumulating changes in elevation from a miles. That a could be anywhere. It could be half a mile, it could be a mile, 1.3 miles. And we want to start accumulating elevation starting at a, and then have a function, so that the function then gives the total accumulated miles starting from a miles from the coast to any number of miles from the coast x. Okay, so we want to distinguish between the idea of amount. The amount is just elevation above sea level. It's an elevation, that's our amount. And then accumulation as we want to start accumulating elevation from some place inland, right? We want to start accumulating changes in elevation starting a miles inland, and then the function then will give us the amount of accumulated miles starting at a until any distance from the coast x. Okay, so can you write that function using R? So can you write that function, that exact, or the function f that gives the exact accumulation of elevation starting from a miles to x miles from the coast? Can you do it? We should be able to. So think about it, try it, and then if you can't, get some help. Okay? What do we know? We just know R. All we know is R. Just pretend. All we know is this rate function, and we want to write this accumulation function, starting from A, ending at X. Okay, volunteer. Let's see. How about right here? Very nice scarf. Did you get this? Okay. Okay, so like R of x plus h minus R of x over h? Is that kind of something like that? So that's actually forming what? That's forming change in rate over change in miles. So that's actually forming a rate. So that's like a rate of a rate. Do you see that? Okay? So, yes ma'am. We want r of x. Just so we need a different variable, right? That's it. So this function is the integral from a to x, the accumulation. This is the accumulation function starting at a, ending at x. And let's just quickly review why that's right, what that means. What is the integral sign stand for? What letter is it like? S for sum, right? Sum. Okay? And this is our integral form, is our open form. Open form meaning it reflects process. Okay? It reflects process. Okay, so the sum, right? So that S stands for sum. Sum of what? Are we summing up rates? Are we summing up rates? No, we're not summing up rates. The dt is part of the math. Okay, that's part of the math. It's not just saying, oh, we're going to do it with respect to t. dt is what? A little change in miles. That's important. That's part of the math. So what are we summing up?
Values from a to x.
What kind of values? Accumulated amounts of elevation. And those accumulated amounts of elevation, in this case, so we call those bits, right? Bits. Those bits, each one of those, what? M dx, right? The rate times a little change gives us a little change in elevation, right? dy equals m dx. That's essentially dy, or a little change in elevation. And we know that dy equals m dx. Okay, so that is reflecting. We're summing up a bunch of little bits of elevation starting at a, ending at x. And each one of those bits of elevation is calculated by m dx. Okay, all review of important stuff from a while back. Okay, so now, how can f also be written in terms of our amount function? So how can we write this accumulation function in terms of our amount function, our elevation above sea level function, which we call E? Okay, go. Think about it. If you need help, then talk about it. How can we also write that accumulation function using this amount function of elevation above sea level? Okay. How about in the hat? Are you gonna tell me? He wants E of x minus E of a. The elevation x miles from the border minus the elevation a miles from the border. So I see some nods. That's right. That's right. So we have the total elevation, the amount of elevation at x, the amount of elevation at a, the difference of those two. So I can come over here and do just wherever my a was, somewhere around here. I don't know, somewhere about there. Okay, so my a, my x. And so if I know the actual elevation a miles from the border, and how is that represented on this graph, that elevation at a miles? Where do we see that elevation on this graph? The y coordinate, which is found where? Where, if you wanted to get an estimate for that number, where would you look? The y-axis, right? You'd look over here. So right over here is our representation of E of A. Okay? And then x. Same thing. At x miles from the border, we could look over here and we'd have E of x. And so it makes sense then, if here's our elevation at a miles from the border and then at x miles from the border, what is our accumulated amount of elevation from a to x? Right? It would be this much. E of x minus E of a. Do you see it? It'd be that change in, that's like a total change in y, right? A total change in elevation. Ex minus E of a. Okay, so two different, in open form, we can sum up bits of little changes in elevation using the rate function. That's open form, that's integral form. Or we can just look at the total amount of elevation at the end and subtract the total amount of elevation at the beginning. Okay? And that's, if we knew what E was in closed form, then this would be closed form for that accumulation function. This would be closed form. If we knew what E was. Okay, so this may be the end of this slide. Is this all familiar? Does it maybe make more sense than before? Hopefully. Really important, right? So this is really the basis of the fundamental theorem of calculus. This is the basis of it right here. Two ways to get a total amount of change. Process, little bits of change added up together, left side, or just total final amount minus initial amount. Two ways to get a total amount of change. That's what the fundamental theorem is all about. Okay? The accumulation of small changes in elevation from A to X miles from the border equals the total change in elevation from A to X miles from the border. This is what the fundamental theorem is all about. Anybody have a question? Okay, so here's that exact same thing. I just more in a little more generic form. Little lowercase r and f. Okay? So the accumulation of small changes of a quantity from A to X equals the total change in that quantity from A to X. This is the principle behind it. Okay. So we get that we have this f of x, and we think of this as an amounts function, okay? So this is just, it's tracking the amount of something. And from that amount function, we can get the rate of change function. What's the rate of change function? 6x minus 1. You guys are masters, right? You're masters of derivatives. The rate of change function is 6x minus 1. Okay? That being the case, so now here's an accumulation function. I want to start accumulating at 4 according to this rate. I want to start accumulating at 4 according to this rate. Well, it would sure be nice to have this accumulation function in closed form. How can I do it? Can I get this accumulation function in closed form? Yeah. Okay. So we haven't started talking about antiderivatives quite yet, but what's the principle here that's going to allow me to get this thing in closed form? Yeah, so I've got the amount function from which this rate came, right? I've got that amount function. I can use that to build the accumulation function. Okay, and it's going to be f of x minus f of 4. So if f is the amount function for that rate, and now I've got this accumulation function that is accumulating at that rate, then I can use the amount function to build this accumulation function. It's going to be the final amount minus the initial amount, f of x minus f of 4. And what is f of x? 3x squared minus x. What's f of 4?
44.
Oh, that was fast.
Minus 4.
Whatever that is. 3 times 4 squared minus 4. Yeah, 44. He's right. Okay.
You sound surprised.
What's that? All right, so look what happened. We just found a closed form representation for that particular accumulation function. It's not, you see, it's not the same as the amount function. It's not just the amount function. We just didn't go forward and back. We used the amount function to get it, but now this is a particular accumulation function starting accumulating at 4, and that requires that's going to be the final amount at x minus the initial amount at 4. So then we get this, 3x squared minus x minus 44. So let's write that out. Just a little more. 3x squared minus x minus 44. All right, so now we've got open form of this accumulation function, and now we have a closed form, right? Rapid fire Easy outputs, right? A nice polynomial, we can just put in values of x and get the amount of accumulation starting from x equals 4. Okay, another example. Maybe you recognize that amount function. What is that amount function? Amount of what? Volume of a sphere. That's the amount of volume in the sphere for a radius of, oh, so it should be, sorry, this should be x. Okay, so for a radius of x, that's going to be the amount of volume of a sphere with radius x. Okay, and what is the rate of change of volume of a sphere then? What is the rate of change of volume of a sphere? 4 pi x squared. Okay, it's a function of x. I could have said f of r, and that'd be 4/3 pi r cubed, and r f of r x, or r. Too confusing. Use x for the radius, right? Use x for the radius. Okay. So now, here comes this accumulation function. What is this? So tell the person next to you, what is this accumulation function about? What are the details of this particular accumulation function? Go. Tell the person next to you. Tell me, what does that mean? Okay, so just tell me about that accumulation function. Somebody, what is that accumulation function about? What do you think? Somebody new. What's that? Well, that's what's equal to, but I want to know about that accumulation function. Yeah.
Accumulating small bits
From 10 to x, bits of what? Okay, change in what quantity? This is accumulation of what? Radius or volume? Volume, right? So this is the rate of change of volume. And if we multiply that by a little change in radius, we're going to get a little bit of what? This whole thing is a little bit of volume. So this is an accumulation function. It's accumulating starting from a, so what is 10? What does 10 represent? A volume? Radius or volume? That's a radius, right? So starting from a radius of 10, this is going to be the accumulation of volume to some new radius x. Okay? So at 10, how much accumulation will we have? What will the value of this accumulation function be when the radius is 10? 4/3 pi 10 cubed? He says yes. What will the value of this accumulation be when the radius is 10? It's not that. Oh, important question. What do you think? Yeah. Will it be 0? This is it's the accumulated volume starting from a radius of 10 to x. Therefore, when the radius is 10, the value of that function is 0. Does that make sense? When we start accumulating at 10, that means we have 0 at 10. We have 0 volume, right? So yeah, there was volume already there, but this function is saying how much new volume do we have as the radius grows from 10. Okay? So how much accumulated volume starting from a radius of 10. Okay, now we want to rewrite this in no longer an open form. How can we do it? Right, we want if we just had the final volume of the sphere minus the volume of the sphere at 10. That'll give us the amount of increase of volume starting from a radius of 10. Okay? So we can write that as 4/3 pi x cubed minus 4/3 pi 10 cubed. Okay, is this making more sense? Really important stuff. Let's look at another example. Let's look at, let's get some graphs involved here. Anybody have a question? Key point that when the radius is 10, the sphere has volume, but this function is 0. Because this function is saying how much accumulated volume since the radius was 10, if it's growing. Okay, starting from a radius of 10. That's why it's a different function than the amount function, right? It's a different function. It's the accumulation starting from a radius of 10. Okay, so how about this one? A little bigger. So now I've got this rate function, 1 over 1 plus x squared. Okay, I want you to represent an accumulation function that accumulates at this rate that is starting accumulating at x equals 1. Can you represent an accumulation function starting at x equals 1? And can you do that in open form and in closed form? What's different about this question than the previous two? It's a big difference. Yeah, R of x is the rate of change. So I want to represent the accumulation function that starts accumulating at x equals 1 and accumulates at this rate. So open form should be no problem, okay? So everyone write down open form. Go. Okay, somebody new. Did you get it here? Drinking the water, Sun Devils? 1 over what now? 1 over 1 plus t squared? Okay, that's, what's that? dt. Agree with that? Shaking her head. In the corner. The integral. The integral of what? So let me start over here. The integral from? So to remind you, integral is Control Shift I. And then you can just fill in the blanks. Of what? 1 over? Okay, 1 over t squared dt. What do we think? Okay, yeah. That's the accumulation function. It starts accumulating at 1 according to this rate. By summing up bits of change, right? By summing up bits of change, each bit m times dx. Each little bit m times dx. Okay? And I can graph that. So what's one thing when I graph this, what's one point you're going to know for sure? When I graph this, what point do you know for sure? When x equals 1, y equals 0, right? Because it starts accumulating at 1. Did it work? Yep, at x equals 1 right there. Y equals 0. Okay. All right, now how about closed form? So here's where we come back to my original question. How is this different than the previous examples? I didn't start by giving you the amount function. All you have is the rate function. Okay? So what do we need? We need an amount function that has that rate. We need an amount function that has that rate. And so here's where your mastery skills also come in. Not just for finding derivatives, but given a rate function, can you know the corresponding amount function, which you all should know. What is it? Arctangent. You should recognize that this is the amount function that gives you this rate is arctangent. So how can I write this same accumulation function in closed form? Final amount minus initial amount. Total amount, right? Final minus initial. What will it be? Arctangent of x. So for arctangent, arc cosine, it's a tan. A sine, a cosine. And you'll know you get it when it flips out of italics. It flips out of italics. Okay? Of what? Is that it? Minus a tan of 1. Right? The sum of many bits of change starting at 1 is going to be the total change minus the total amount minus the initial amount at 1. Okay, so let's graph the first open form in red. And now when I graph the closed form in blue, what should happen? It should be exactly the same if we got it right. Boom. Landed right on top of it. So this is why you practice, for your written homework for tonight, you practice what we call antiderivatives. Given a rate function, can you come up with an amount function that has that rate? That's just all. It's not a new set of rules. It's just learning to think backwards from all the mastery rules you've already learned. We're not learning a new set of rules. We just know the rules in forward. Now we have to do the rules in reverse. We have to recognize that. We have to recognize that we have a rate function. What would that amount function be? Okay, now just one side note I'm going to note here. We're starting accumulating at 1, right? So it's 0. But what do you notice over here to the left? We still got a bunch of graph over here, right? So the way we've been talking, it's kind of like we were just saying this. The way we've been talking, it's like, okay, we're going to start accumulating at 1, right? But if I take away that domain restriction, I still get a valid, for this accumulation function, I still get valid values for all input. So we want to kind of just tweak our language a little bit, and we're going to think about, so really, we're still accumulating before 1 even, but then what happens? We get like a reset at 1, okay? So we want to think of this, rather than starting accumulating at 1, there's already been accumulation going on. And so now we want to just tweak it a little bit and say, by integrating from 1 to x, we're gonna assure that we get a reset of 0 value when x is 1. But there is accumulation going on before, not just after 1. Okay. So we're gonna kind of change this to with a reset at x equals 1. Okay. The reset at x equals 1. Why? Because this accumulation function still has values before 1. Okay, we still have accumulation. It's just we know for sure that when we get to 1, it's like we're going to start over and start from 0. Okay, start from 0 and then accumulate from there. Okay, cool. So let's try another example of that. Here you go. So here's another, this is practice from your written homework. So here let's just do that bigger. Let me make that bigger, hold on. Okay, so there's your rate function. I want to represent the accumulation function that has a reset at x equals negative 2.5. And I'm going to do that in open form, and I want to do it now in two ways in open form. I'm going to use function notation and also use the function rule, because both are valid. Okay? So when you write your open form, two ways. Using function notation, using the rule. And then in closed form, and again, if you had calculus before and you learned some kind of technique to do this, try to forget that and try to think about it as, okay, I just finished this problem on the mastery test. What was the function the amount function I was given that I ended up with that as my derivative? Okay, what function has that as its derivative? That's the way you want to think about it. Go. You got some work to do. Okay, how about let's open form. So open form using function notation. Ready? Did you get it? First one? Did you get it? Open form, integral of, okay, integral from negative 2.5 to x. That's it, dt, right? That's using function notation, right? Where r of x is defined as this rate function, okay? How about, again, in open form, but using the rule? Again, in open form, using the rule. How about right here? Uh-huh. Any more? Right, that was a mouthful, I know, sorry. Good job. Exactly right. That right there. So those are your two open forms. They're exactly the same because r is defined as that rate function. Questions on that? Okay, so now in closed form. Yes, sir?
Sine x to the 403 minus sine of negative 2.5 403.
Okay, so you came up with an amount function of what?
Of the rate of change.
Yeah, and which was?
Sine x to the 4 thirds.
Sine x to the 4 thirds. Okay? So here's the beauty of this. If you make a stab at it and you're not sure, what can you do? Take the derivative of your guess. And then if it's right, what should happen? Should be exactly the rate function you were given. Okay? So don't be afraid that you have to get it right, perfectly. Just make a stab at something close, and then forget about what you started with and do it like it was a mastery test derivative, and then compare what you get to what you started with. If it's a match, then you know you got it right. If it's not quite a match, then it will help you to adjust. Do you have a question? Yeah.
So f of x minus f of negative 2.5, is that not an open form way of writing it, or is that just?
But it is an open way for writing it, but we can do better because we know what f is. Right? So yes, that's fine, but we know we can do better because we know what f is. It is sine of x to the 4 thirds. And what happens if we graph the open form and the closed form? Should be the same. Should. Here's the open form. And here's the closed form. You don't see anything new because it's the same, right? What about at x equals 0? Is that remember we talked about cusps, right? A cusp it's a critical value, and what's true about the rate of change at a cusp? Rate of change at a cusp or a corner point, right? A corner point. What about the rate of change? 0? Does not exist, right? It does not exist. So what's happening at x equals 0 here? Do we have looks like maybe have a corner point? Does the rate of change exist at x equals 0? What's that? Tell me. So, what do you get? Okay. And is that valid or not? Is R of 0 valid? We get 4/3, 0 to the 1/3 times cosine of 0 to the 4/3, which is 0. Valid or undefined? Oh no. What's undefined about that? Cosine of 0 is it's not 0. Cosine of 0 is our horizontal distance to the right of vertical diameter for an angle of 0, which is 1. 1. This is 0 times 1. So the rate is 0. It's not undefined, it's 0. And if we zoom in, what should we see? It's not a cusp, right? It should look like what? What does a rate of change of 0 look like for the accumulation? Pause. A pause, right? It was going down. So it kind of looks like, all right, so now we're separating here. Didn't like that. Okay, so as we zoom in, what we would see is it's going down, and then it pauses, and it's going up. So it'd be a smooth low point. There would not be a corner there. Okay, that's verified by the fact that if you plug 0 into the rate function, you get 0. It's not undefined. Okay. So let's summarize the fundamental theorem of calculus. F is any antiderivative of little f. Okay? So we can think of capital F as the amount function. Okay? Then the integral from a to x of f of t dt is big Fx minus big Fa. Okay? The sum of lots of little bits of change is equal to the final amount minus the initial amount. The sum of lots of little bits of change equals the final amount minus the initial amount. Okay, so for a particular value of that function would just be like plugging b in for x. Okay, then you would have the integral from a to b. And then you would have what? The final amount at b minus the initial amount at a. So this is just, this version of it is just picking a particular output value, picking a particular value for the independent variable x, b. Okay, so then rather than having a function, we get a total amount of change, right? A value, right? So this is that value as a sum of lots of little bits of change, and this is that value as a final value minus an initial value, or a total amount of change. But in the second, we're talking about actual numbers now. The first is our functions, right? It's a function. Okay, so this property has enabled generations of people to do calculus exercises without understanding calculus. Okay, so but have gone after something much greater than that, right? We've worked hard on the meanings of everything in terms of amount, accumulation, rate of change. Okay, and now thinking about A as our point of reset, right? Our point of reset, where we're going to start accumulating. We're going to start accumulating, or we're going to reset the accumulation. Okay. Again, the accumulation function represented in open form for a quantity with rate function little f and a reset at x equals a. Okay? That's what that means on the left. On the right, that same accumulation function, which we can now represent in closed form if we can get a closed form for the amount capital F. Okay? And so for us, that's going to be about knowing the rate using the mastery test rules in reverse, right? Knowing the rate, thinking backwards from the mastery test, that will give us a closed form for the amount, and we can write a closed form for the accumulation. Okay, any questions on this summary of this kind of this pinnacle of the course, right? So we've spent maybe 75% of our time so far in the course building up to this theorem, the fundamental theorem. Anybody have a question? Okay, so here's another notation that we'll see. So when you're talking about evaluating the amount at B minus that the amount evaluated at A, you also see it this way sometimes. Just the function with a vertical line, and then x equals b on the top, x equals a on the bottom. What does that mean? That means just this up here. Evaluated at B, evaluated at A, and subtract. Or total change, right? Total change of capital F. So that's what that notation means. It's a kind of a shorthand way of writing this. Oftentimes you'll do this first. So from here, you'll be given a open form accumulation, and you'll start by writing this. Write your amount function, and then signify that you're going to evaluate it at B, evaluate it at A, and subtract, which is then this.